This week we're going to round out multiple regression by talking about centering scores, the effect sizes, partial and semi-partial correlations, and what they mean and when we'd use them, and then some of the additional issues we need to be very aware of when we're doing multiple regression, especially with more complex models, and we're going to end up on actually the process of model selection. Now again, all of these processes are things that we've discussed in the past. We're just going into a little bit more detail and really just reinforcing that knowledge, as multiple regression is kind of the kitchen sink of statistical techniques. There may be statistical techniques that are more appropriate than multiple regression, but multiple regression can handle almost any methodology as long as we're predicting a single continuous outcome. So centering the scores, it's a good idea to center your scores, especially if you're expecting interactions. And the reason for this is it makes the interactions a little bit easier to interpret. However, mathematically, there is no need to center scores. In other words, no matter what your original scores were, your measures, whether they're predictors or outcomes, on a continuous scale, the actual analysis of how much variance is being explained is independent of the scale of measurement. So by the time we're done actually calculating our R and our R squared, our beta, or whatever we're looking at to look at individual predictors, it really doesn't matter if they've been centered or not. So the process of centering is more of a choice. Now, this is another one that you may want to just simply talk to the person that you're working with or the person that you're doing a multiple regression for, or who your advisor is. If they expect you to center scores, then by all means you should. I am simply stating that there's not a requirement, it's simply a method of making it easier to interpret the results of a multiple regression or a more complex model, especially if we're talking again about interactions where we're having to look at how various measures that might be on different scales interact with each other on our outcome. So scores are often centered to make these tests easier to interpret. Centered scores are rescaled so that the mean of the distribution is 0. So we subtract the mean from each score to obtain a deviation or centered score, and then we compute the regression equations after centering. So a lot of times we'd actually create new variables, for example in SPSS. So if I had a measure of depression, I wouldn't change that measure to a centered score. I would create a new variable, centered depression. And how I'd create that is I would simply find the mean of depression and then subtract it from every single individual score someone had in depression to create those centered scores. Under this new scaling, now if you have a 0, you're in the mean. If you have a positive number, you're above the mean. And if you have a negative number, you're below the mean. And that kind of helps us to interpret what these kind of interactions look like. Once you have done that for any of the continuous variables that you're expecting to have interactions, or all of them if you're expected to by your advisor or the person you're working with, you would compute the regressions using these centered variables, not the original variables. Now again, mathematically, there is no difference in the variance or variance explained. This doesn't change any of the equations we're going to be conducting. It simply means that the outcomes tend to be a little bit more easy to interpret because you now have a base rate of knowing that instead of having to actually look up the mean and go, oh, this person actually has a score above the mean, this is kind of a positive relationship, you can tell by whether it's a positive or negative number. Positive numbers above the mean, negative numbers below the mean. So for example, our original data might be on a 0 to 100 scale. The mean is 50, the standard deviation is 12.5, a minimum score of 0, a maximum score of 100. We basically subtract the mean from each score. We get a center data. Now notice that the center data, it isn't the same as a z-score, because z-scores put the actual scores, again, a 0 on a z-score would be the mean. But z-scores go beyond centering. Z-scores also force that distribution into a normal distribution to where the numbers are now also equivalent to standard deviation units. So a z-score of +1 is 1 standard deviation above the mean. A z-score of -2 is 2 standard deviations below the mean. We do not create that kind of standardization when we center. All we're simply doing is whatever the scale is, we're moving that scale to where the midpoint is 0. So once we centered this data set, Our mean instead of 50 is now a 0, but our standard deviation has not changed, it's 12.5. And our minimum, negative 50, to our maximum of 50, when originally our minimum was 0 and our maximum was 100, is the same range. We haven't changed standard deviation, we haven't changed range. We've simply renumbered it to where 0 is the midpoint. Negative numbers below, positive numbers ahead. And you can kind of see why some people like to center scores. We really haven't changed the scale of the measurement or the meaning of the measurement. We've just made it very easy to identify when we're above or below the midpoint with an individual score. So if we actually have interactions, we need to do simple slope tests. So tests for simple main effects is another way to think about this. And the algebraic equation from Aiken and West is basically the b weight of 1 plus the b weight of 3 times x2 multiplied by x1 plus the b rate of 2 plus the score on x2 plus the b of the actual intercept. So I'm going to walk through what that equation means and how to do it a lot easier on the next slide. But basically what we're going to be doing is we're going to be computing separate equations, separate prediction equations using data at each level. And typically what we would do is we would choose the second of the two continuous variables that interacted. So again, what we're doing is we're exploring an interaction. If we're exploring an interaction, that means that we had two predictor variables that when we created an interaction term, we multiplied the two variables by each other. That new variable actually explained variance above and beyond what each variable explained by themselves. So there's more going on than just the main effect of the first predictor or the main effect of the second predictor. There's also an interaction between those two predictors. But now we have to find out what kind of interaction, what does it look like? And unlike with an ANOVA, where we're simply comparing the means of blocks, we're now looking at actually linear regression equations. We're looking at linear prediction on our predictor. So what we need to do is to basically hold constant one of those predictors. Usually it's going to be the second one. And how we hold that constant is that we use the mean for the second predictor for one of these simple slopes. We use one standard deviation above the mean of the second predictor for one of these slopes, and we use one standard deviation below the mean for that second predictor for the simple slope. So what we're doing is we're holding constant one of the two predictors to then create a prediction equation for our outcome at each level, one standard deviation above, one standard deviation below, and the mean of our second predictor. So let's look how we actually do this through hand calculation in the next slide. So suppose we have an interaction between two IVs, and our DV is extroversion. Our IVs are depression and internal locus of control. So we're trying to predict extroversion. Extroversion in this case is Y prime. We're trying to predict someone's extroversion from their depression and internal locus of control scores. However, we also know there is an interaction. So there is a significant effect of depression, there's a significant effect of locus of control, and there's a significant effect of the interaction between depression and locus of control. So in this case, to explore that relationship, we need to hand calculate simple slopes. So the first thing we're going to do is we're going to find the three simple slopes, locking the mean of our second predictor, in this case internal locus of control, to either mean one standard deviation above or one standard deviation below the mean. So for that equation then, we'll look at the first one. We've locked mean of extroversion, x2, so x2 represents the individual scores at extroversion at a 0. We've centered these scores, and that's one of the reasons centering scores can be a little easier in these situations. Therefore, we know that the centered score, the mean, is 0. So we're going to calculate our prediction of how do we predict someone's outcome on extroversion if their locus of control is the mean, a 0. So to do this, we're going to simply bring some numbers down. First, we're going to bring down the B weight for depression at the start of the equation, negative 0.48. And notice that for all three of these equations, that number doesn't change, that number doesn't move. Next, we're going to bring down the B weight for locus of control. This number also does not change or move, and it is in the same location, and it's the same number in all three of these equations. We're going to bring over the actual B weight of the interaction of depression and locus of control, and once again, notice that 2.17 is the same and in the same position in all three of these equations. And finally, we're going to bring over the a or the y-intercept. And again, it's going to be at the end of each of these equations, and it doesn't change either. So that leaves us what does change. Well, what changes is the person's score on x2. So we're adding that in. So in the first equation, it's going to be 0. So it's the mean. It's been centered. So it's going to be 0 and both locations that it would show up in, both the interaction and its individual effect. On the second equation, we're one standard deviation above the mean of locus of control. Turns out that that happens to be 0.16. So now we put in 0.16 where those zeros were, and we run the equation again. And finally, we do the same for one standard deviation below the mean, in this case, negative 0.16. And again, this is where that centering kind of helps us to kind of mentally figure out what we're doing. So we're going to get 3 different strengths of prediction for this person based on whether or not someone had a high locus of control, a mean locus of control, or a low locus of control. And the strength of those predictions is going to tell us what those simple slopes look like. So if we actually graph the simple slopes for everyone in our sample, what we'd find is here's how that interaction is working. That at low levels of depression and high levels of extroversion, there's very little difference in internal locus of control. However, as we move to higher levels of depression, locus of control is now a big predictor in someone's extroversion. So if you have high locus of control and high depression, you tend to still be somewhat extroverted, though a little less than if you are not depressed. If you're depressed and you have the mean level of locus of control, your extroversion is actually below the mean. It's getting lower, it's smaller. And finally, if you are heavily depressed and you have a low locus of control, external control, you actually have a much lower relationship now. Your extroversion is much lower. So how depression and locus of control combine to predict someone's extroversion changes based on their level of depression and their level of locus control. In other words, what we find from this chart is that locus of control really doesn't matter at a low level of depression. So if you know they're depressed and they're not very depressed, it doesn't matter if they've got an internal, external, or medium locus of control. But as they become more and more depressed, locus of control becomes more and more important. So the next thing I want to talk about is the 2 ways to define the effect sizes between particular predictors. An effect size becomes somewhat difficult when we're talking about individual predictors because we're looking at a more complex model than just one predictor on an outcome. So for instance, in this particular model, I have 2 predictors, x1 and x2, and they're predicting y. And there's a lot going on in here. So for example, D is the variance between our predictors that are related to each other but are unrelated to our outcome. B is shared variance between our 2 predictors that is predicting our outcome. F is the variance in x1, our first predictor, that has no relationship to any other variables, and that's the same for x2. E is the unexplained variance in y that's not being explained by either of our predictors. And then A is unique variance predicted only by our first predictor in our outcome y, and C is unique variance explained only by our second predictor in our outcome y. So if we're wanting to actually define and discuss effect size, we first have to decide exactly what we're wanting to talk about, and generally there's 2 types of effect sizes we discuss in this situation: semi-partial or part correlation, or partial correlation. So again, we are reminded that scientists and mathematicians specifically, and statisticians in extreme specifically, are not very good at naming things. So there really is semi-partial or part correlation is different than partial correlation. That's just something you're going to have to just repeat and get used to. So for example, if we are predicting years of marriage by commitment and intimacy, if we were doing semi-partial or part correlations, what we'd be looking for is what is the unique prediction, unique variance explained by our predictor in the sum total of our outcome. So that would be A over A, B, C, E. In other words, how much of years of marriage in total is predicted by just commitment. And for intimacy, our semi-partial or part correlation would be C over ABCE. So again, what is the unique variance only explained by intimacy in the total variance of years of marriage? For a partial correlation, we're simply asking what is the unique variance over the unexplained variance. So that, in this case, would be for commitment, A over A plus E. What's the unique variance explained by commitment in unexplained variance of years of marriage? In other words, ignoring variance that may be being explained by other predictors. And intimacy in this case would be C over C plus E. So again, a way to think of this is, visually speaking, if we're talking about semi-partial or part correlation, we're simply asking what is the unique variance explained by a predictor in all of the variance of our outcome. If we're talking about partial correlation, we're asking what is the unique variance explained by our predictor in the unexplained variance of our outcome. In other words, variance that isn't explained by any other predictor. Now, which you use really depends on what you're really wanting to talk about. If you're really wanting to focus on one predictor and one predictor alone, you might talk about semi-partial or part correlation. I personally prefer partial correlation because it gives us information about each individual predictor in isolation, but also then we can figure out, based on that, how much total variance are we explaining. So partial correlation estimates the unique contribution of a predictor to the unexplained variance of the outcome. Contribution to the other predictor is removed and the outcome from the outcome and from predictor 1. So in this case, our actual calculation is the proportion of unexplained variances. Simply, we can also calculate that by what's left. Semi-partial correlations estimate the unique contribution of a predictor to the total variance of the outcome. So the contribution of the other predictors is removed from predictors, but not from the outcome. And again, we can calculate at that point what is the total variance, the DV, uniquely contributed to by the IV.